Okay? All right, so it says find a formula. Now, okay, this is on the, this is the first of the two 4.2 assignments. So this one really is just kind of getting you ready, practicing all the skills needed to find the Riemann sums. And we'll go through, really all I want to do today, if we go through this and then maybe go through a sample of a Riemann sum problem where we're going to find the exact area under a curve by setting up a sum of rectangles and then taking the limit as the number of rectangles does what? Goes to infinity. Yeah, good. And that'll get us the exact answer. And then I'm going to give you a day to kind of work on that stuff some more tomorrow. Where I want to be before we go to spring break, I want to get to the calculus tricks before we get to spring break. That'd be a great. If we can get there, we're in good shape. And that's the very next thing we would do. Section 4.4 is just learning a much easier way to do this stuff. And that's the reward at the end of the week, is you get to abandon all this complicated sigma stuff and go to something simpler. Well, hey,
it's not.
You could call it that if you wanted to. So we want to do this right here. We want to just simplify that, right? And so we have to look at this. I mean, this is kind of a longer process. Remember that we're just going to kind of work from the inside out. So on the inside, we've got this sigma function, first of all, that we've got to add up using our summation rules. We only have 4 of them, right? We know what the sum of a constant is. We know what the sum of I is. We know what the sum of I squared is and what the sum of I cubed is, right? And then once we've taken care of the summation part, then we move outside. We take the limit of that as n goes to infinity, right? So there's really 2 layers to this. The sigma is acting on the i's. That's the variable of the sigma, the variable of summation. And it's spitting out answers in terms of n. And then the limit is sensitive to n, right? The limit is acting on the n's, letting n approach infinity. So let's focus on first things first here. So we need to find, we'll leave that for later. Sum of I plus 2I, oh no, 1, sorry. 1 plus 2I over n quantity squared times 2 over n. Okay, so first of all, let's do some color coding here to make this thing really. Okay, so the sigma is acting on the i's. Remember that we have some properties of sigma notation. We looked at some stuff last week where we said if we ever multiply, if we do something like this, right? If we say the sum of some constant times some function of I, as I goes from like 1 to n or something, what can we do with that constant?
Move it out front.
We can move it out front because it's just going to be multiplied by every term that we get. For every value of I, when we evaluate the, each of those numbers, right? For I equals, 1 up through whatever we're going to, they're just going to end up being multiplied by that constant. There are no i's in it, so it never changes, right? So for one thing, what could we do with this, I guess, is what I'm getting at. Yeah, there's no I in that, right? It's just a 2. We don't have to, by the way. We don't have to do that. It's fine. We can leave it there. But it sort of unclutters things if we move it maybe out in front of that sigma. So we don't really have to worry about it. We can distribute it through later, right? So that maybe helps just a bit. So then we're left with the limit as n approaches infinity of 2 over n times a bunch of stuff. Well, what's this going to become? This 1 plus 2I over n quantity squared. How are we going to deal with that? Yeah, we gotta FOIL that out, don't we? Because what we really need to get out of this, remember, is we need to write this as a sum of terms, and each term is just gonna end up having one of these summation formulas. What's the sum of a constant as I goes from 1 to n? Cn. What's the sum of I as I goes from 1 to n? N times n plus 1 over 2, good. What's the sum of I squared as I goes from 1 to n?
N plus 1, 1 plus 1, 6.
Good. And then finally the sum of I cubed that goes from 1 to n. N squared times n plus 1 squared over 4, I think. Yeah, and these are all, and you have all those in the book, right? So you have all those available.
That's the only reason I got that.
But we gotta be able to get sum of terms in our sigma that just are, are broken down into powers of I. So to get there, we need to expand this out. So we get the sum of 1 plus, what are we gonna get when we FOIL that out?
1. 4i over n.
Yeah, but I agree, 4i over n, because it's like if that's an a and that's a b, we get a squared plus 2ab. So 2 times 1 times 2i over n is just 4i over n, plus the quantity 2i over n squared. Right? Okay, and I'm not going to write the I goes from 1 to, we just know that's part of the sigma, right? And so then we get what do we get from this one? What's the sum of 1 from 1 to n? From I goes from 1 to n. N, right, good. So that gives us an n plus, how about that one? The 4 over n, I can pull out front, right? And then I've just, really what I've got is 4 over n times the sum of I. You see that? Let's, I'm gonna add I'm gonna add one more row here. I feel like I need to. Oops. Let's add one more row here. So then we get sum of 1 as I goes from 1 to n plus 4 over n times the sum of I from 1 to n, right? Plus 4 over n squared times the sum of I squared. Right. Now we'll plug in the results of those. Those are, we know those summation formulas, right?
Yes, we do.
Okay. So we get 2 over n times, this one's just going to give us n. You told me that a second ago, right? Right there. This one's going to give me 4 over n times, well, you just told me that, right? There it is, right there. Plus 4 over n squared times n times n plus 1 times 2n plus 1 over 6. And once again, you just told me that right there. Right? And now look what we did. It's actually a lot better now. We got rid of all those sigmas. Now all we have are a bunch of n's in there. right? We got this big, long expression, bunch of terms added up with n's in them, and then eventually we're just gonna take the limit as n goes to infinity. That'll be our answer, right? Okay, so let's go ahead and simplify this. Let's distribute this 2 over n all the way through and expand these out and do all that stuff, right? So what are we left with then? So when we distribute the 2 over n this to there, we just get 2, right? Plus 2 over n times 4 over n is going to, I mean, we could even do this, couldn't we? We could cancel, that's an n that's a factor on the bottom, right? Because the bottom is just n times 2. The bottom is 4 times n times the quantity n plus 1. And so we could cancel those, right? And then if we distribute the 2, and we could do that, that's a 2 and that's a 1, right? Now when we distribute this 2 over n through this term, we're going to get 2 times 2 on the top is 4 times n plus 1 all over n, right? Okay, what about here? Let's see, we could cancel one of those n's. We could reduce this to a 2 over 3, and then when we distribute this guy all the way in, we get what? 4 times the quantity n plus 1 times 2n plus 1 over 3n squared. Good, because we still had an n there. Very good, right? Okay. Now look what's going to happen here. You can kind of see the writings on the wall. You know what's going to happen. I've got to do one more, whoops.
Why is the n squared in the absolute?
Say it again.
The term on the right, why is the n squared on the bottom?
The n, well, because look, n squared is just n times n. And so n divided by n squared is the same as just 1 over n.
Yeah, so why is it squared then?
Oh, because I distributed this 2 over n all the way through. Yeah, there you go. Yeah. Okay, so look what's going to happen here. We're going to have to still. I'll say it again. Okay, so it's better, right? Now, in each of those, if you look at each of those separate polynomials, the top is a polynomial with a degree of n in this case, top and bottom, n squared in this case, top and bottom, and that's just a constant. So when I rewrite this, what's going to end up happening is, when I take my limit, all the n's are going to go away and only a couple of constant terms are going to remain. And maybe that's not abundantly clear to you yet, but that's something that will be. As you do a few of these problems, you'll kind of get an idea how that's all going to play out when you do the algebra. So let's do that. Let's go ahead and expand out the tops, right? And then and that helps. So we end up then with the limit as n approaches infinity of 2 plus, if I distribute the 4 on top, I just get a 4n plus 4 over n. Right here, I'm going to get, if I FOIL this out, distribute the 4, I'm going to get what? 8n squared plus 3n, so plus 12n plus 4 all over 3n squared. And if I split these into separate terms and divide them all out, then look what happens. So I'm going to get 2 plus, if I split that into separate fractions, what do they simplify to? What's the first one going to be? 4. Second one? first term? 8/3. Second term? Good. Plus last one? Good. And now, no ends on the top anywhere, right? The only ends that survive are in the denominators of fractions, and so what's gonna happen when we take our limit as n goes to infinity? What happens to this term? 0. This one? 0. 0. Right? Right, makes sense. And so we end up then with only these constants surviving, and so our area, or we don't, I guess we never even said it was an area. Our original expression, if we go back a couple pages, whoops, right there, I guess. When we simplify this thing, we're just supposed to get, well, I guess they want you to write it out. Okay, look right there. There's, we were supposed to expand this as a limit, simplify it as a limit in terms of n. So that's our answer right there, isn't it? Right? See what I'm saying? Before we actually took the limit, we've got the limit as n approaches infinity. So all that stuff before we eliminated the terms is what you'd be writing in there. We can distribute the two. You can distribute the two, and it should still be fine. Okay? And then we want the answer, finally, what is the numerical answer when we take our limit? Well, when we take our limit, we just get whatever 2 plus 4 plus 8/3 is. So that's 6. 6 in terms of thirds would be, what, 18/3 plus 8/3 is 26/3. Okay. And so the only additional piece really that section 4.3 adds is nothing. All it adds is just changes the notation. It just says, instead of starting off with the area defined as f of x and like a picture maybe, it's just defined this way. So if we wanted to okay, all it does is it says I might just show you the trick. When do they do that in the book? They do that. Okay.
So, one second.
Okay, real quick, what was this problem, we'll just use the example we just did, we won't do anything new. With this example we just did, what were we really finding? What did this represent?
A limit, sum is special.
Yeah, we did the limit as n approaches infinity of the sum of this stuff. Well, where would that have come from? If you kind of work backwards, right? Can we relate that to this? Can we say that this is the limit of the sum of f of x, right, times f of x sub I times delta x, right? Can we do something like that, or a plus? Yeah, that's right. That's how we did it, right? Can we think of it that way? Can we write it in a way that makes this look like an area under a curve? Remember that we said if we want to add up the area under the curve, the most convenient way to do it is just to add up the areas of the rectangles defined by their right side. So we made this always look like, we said x sub I is just a plus I delta x, where delta x is just b minus a over n, right? So can we can we figure out, kind of backtrack and figure out, now what was the original problem that maybe just came from? What did we just do? We found an area under a curve equals 26/3, but what was f of x and on what interval? Can we do that? Alright, so this looked like the limit of the sum f of x sub I, so it's got to be f of a plus I delta x times delta x, just equals that. Put those side by side, or line them up vertically, and see, what would f of x have to be? What do you think? It's got to be x squared, doesn't it? Right? Doesn't it? Because whatever we're putting in here, f of hand, in this case, evidently just equals hand squared. Right? So f of x equals x squared. There's the area, we're adding up the area under that curve. From where to where? Well, what's delta x? 2 over n, yeah. So b minus a must equal 2, right? Yeah. Okay, so if b minus a over n equals 2 over n, then b minus a equals 2. What's a? What's hand, I guess, is what we're asking. We know that it's 1, isn't it? Yeah, good, it's 1. So a is 1, delta x is the same thing as saying 2 over n, right? Times I. Everybody see that? Okay, this is a plus I times delta x, isn't it? Right? This looks like there's our I, and here's our delta x. That's kind of hard to work backwards like that, isn't it?
Yeah. It is.
Right? You don't do that very much, which is good news. I mean, it's not like you ever really have to do this, but this one time I want to. So then we find out that if a is 1, then b must be what? 3, yeah. And so what this really represented was the area under f of x equals x squared on the interval from 1 to 3.
Oh.
Okay? Right? Now, wouldn't it have been more convenient if we could have just known that from the beginning? Yeah, it would have, right? So here's the notational shift we're going to make. Instead of having to write all this stuff out, we're just going to write this as a definite integral from now on. Okay, we're going to write this as the integral of f of x dx from a to b. Okay? And that's going to correspond to this, the area under the curve, x squared, on the interval from 1 to 3. So that's going to correspond to, at least for one more day, that's going to correspond to, oh, paper towels, I got you. Okay.
You should just left.
I've had that feeling in math classes before. So for us, it always just corresponds to that for now, right? That's, if we can start off with this, that's what we're trying to find. We have to do this in terms of limits for one more day, and then we're going to come up with a great trick, right? So I want you to practice one time just setting up the limit. So let's how would we do this problem? set that up as a limit? Or as a limit of a sum? Of. So what's A in this case?
2x squared.
2x squared.
Well, A is just 2, right? Good. Okay, B is 7, right? So that tells us that delta x must be what?
5.
5 over n, right? B minus A over n. Okay. Good. Okay. And we know what f of x is. What's f of x?
2x squared.
2x squared minus 3 quantity squared. Okay. Right? That's our function. And so that's a pretty complicated one, isn't it? So if that's f of x, that's a pretty hard one.
Yeah.
That's what we're putting into it, right? If f of x is that, what would f of hand be? If f of x is the quantity 2x squared minus 3 squared, what's f of a? 2a squared minus 3 quantity squared. What's f of z? 2z squared minus 3 quantity squared. What's f of hand? 2 hand squared minus 3 quantity squared. We're not going to do this one. Don't panic. I just want you to set it up. So if hand is always going to be a plus I delta x, right? This is going to work out to just be hand times 2 squared, right, minus 3 quantity squared, right, times delta x, and we know those things. There's that. We know what a is. We know what delta x is. So we could write this whole, once again, we're not going to do this. I'm not going to have you do this one. Don't panic. But we would set this up as the limit of the sum of 2 times the quantity a is 2 plus I delta x. Delta x is 5 over n, you told me, right? So that's just 5I over n squared minus 3 squared, right, times 5 over n. Right? There's okay. That's a pretty horrible one.
Yeah.
And once again, I'm not going to make you do that. We could though. We really could do that, couldn't we? If I squared this out and distributed it 2, it's going to be pretty ugly. But when I square that one out again, my biggest power of I would be I to the 4th. I would get an I to the 4th term, an I cubed term, an I squared term, and a constant. And there'd be a lot of algebra to get it down to that point. But then I could do this one. You could do this one if I made you do it and you had to spend enough time on it. I won't, but you could, right? So one more shot of this, and then we'll come up with a much easier way to do this that you can do much quicker. Yeah.
So does that integral symbol just mean the same thing as the sigma thing, or?
Well, okay. What it means is, good question. Here's a relationship that might make it a little clearer. Sigma means a discrete sum, right? So sigma means, that's a Greek S, and it means sum of. But it always means we're adding up, one by one, we're adding up terms, right? Now, if we take the limit as the number of terms goes to infinity, that discrete sum starts to lose its meaning because you can't really add up an infinite number of terms. And so what this means, this is a lowercase s. So this is like a calculus sum compared to a discrete sum. Compare that to the connection between a delta and a d, right? Think what we use deltas for. Deltas we use for calculating slopes of secant lines, right? Like we would say, remember we said that the slope of a secant line is just change in y over change in x. But when we calculus-ified that, right, and we made this into the slope of a tangent line, we said that is dy over dx, right? Where that distance shrunk down to 0 and it became a continuous issue instead of just a discrete issue. Well, the same thing is happening up here with this. We're taking a discrete sum and we're calculusifying that and turning it into an exact sum. And that's what that integral sign means. Okay? So they represent the same thing. We're just writing this now in a calculus way, right? So on section 4.3, to kind of boil this down, what kinds of problems are you going to see? You're going to start with not that hard, but problems like this. You're going to turn that into a discrete sum in the limit that n goes to infinity. So it becomes an exact sum, right? And then very soon, before the end of the week, we're going to stumble upon a connection between this process and the antiderivatives that we started with in this unit. Okay, and then so in pairing those together, we come up with a great calculus trick. You know, I call it a trick. It's just a shortcut that allows us to add up these areas under curves much more efficiently without having to go through all these steps of doing discrete sums and simplifying the discrete sums. Keeping in mind that this is pretty contrived, isn't it? I mean, we're only doing this for power functions of I up to 4. So what would we do if we had a trig function or something? You know, we'd be lost. It wouldn't. Then it gets much more complicated to do this. My goal is not to make you experts in the archaic way of adding up discrete sums and taking the limits, because that is very hard to do. If you wanted to add up something as simple as the area under a sine curve, you couldn't use, I'll just give you a little insight into why we wouldn't want to do this. Because then delta x could not be uniform. You'd have to define some delta x that got bigger as x changed, but still went to 0 in the limit that n goes to infinity. That sounds kind of hard to do, right? Well, it's honestly not worth doing. So we're moving towards a much better, more efficient way.